This is a lecture course on synchronization, Part 3, Mechanisms of Synchronization. Synchronization is a physical phenomenon which can be described in two languages, in the language of physics and of mathematics. What can we do as physicists? Suppose we observe some oscillatory processes in some systems which interact. How do we even know these systems are oscillating? By registering how their variables are changing with time. That means by recording signals coming from these systems. How can we say if synchronization is taking place during their interaction? By singling out the time scales of individual oscillations from their individual signals and comparing them. The time scales can be detected as either average or most probable periods or as the main frequencies in the power spectra as described in Part 2 of this lecture course. This is a typical approach of experimental physics, to observe the behavior of the devices under study and to analyze their signals. This way, we can establish whether synchronization is occurring or not. However, a simple observation of the phenomenon does not allow one to explain why it is occurring. To answer the why question, we use the language of mathematics, specifically the language of dynamical systems. We appreciate that different oscillatory modes are characterized by different attractors in the phase space of the system. With this, the transition between attractors occur through bifurcations. Now, attractors and bifurcations can be detected by analyzing the phase portraits and the Poincaré sections of the systems under study. Thus, when the parameters of the systems change and a transition occurs from no synchronization to synchronization through a certain mechanism, the behavior of time scales can be explained through bifurcations taking place in the joint phase space of the interacting systems. Consider possibly the simplest case of synchronization, forced synchronization. This type of synchronization occurs when interaction between two oscillating systems is in one direction only. One system knows what the other is doing, but not the other way around. A single self-oscillator can be described as a dynamical system of an autonomous type, which in mathematical notation is represented by this equation. Here, x is a state vector whose dimension is 2 or more, since oscillations can occur only in systems whose dimension is at least 2. Autonomous means that the velocity vector field v of x is fixed in time. To model a unidirectional coupling between two oscillating systems, the simplest way is to take the signal s of t coming from one of these systems and to allow it to modulate the velocity field of another system. Such systems are called forced. We assume that s of t is a signal changing rhythmically in time, and therefore the velocity field of the system being forced is rhythmically breathing. We assume that when there is no interaction between the systems, it means that the signal s of t is 0. This means that any rhythmic breathing of the velocity field of the forced system stops, and this field becomes equal to the original field of the isolated system v of x, when there was no interaction. A paradigmatic example of a dynamical system demonstrating self-sustained oscillations is van der Pol oscillator, which has a limit cycle if the parameter epsilon is above 0. To model the simplest case of a periodic forcing, we include into the second equation a cosine term, whose frequency is omega and amplitude is b. Periodic breathing of the velocity field means that at some time moments the phase velocities increase, thus speeding oscillations up, and at other moments decrease, thus slowing oscillations down. With this, the limit cycle, which existed in the original unforced system, does no longer exist at the same location in the phase space. While the forcing lasts, some periodic orbits might exist in the phase space. they would not be at exactly the same location as the limit cycle of the unforced system, and they could be stable or unstable, and their periods would be generally different from the period of the original limit cycle and from that of forcing. Generally, as a result of forcing, another attractor in the form of a two-dimensional torus is born in the phase space, which means that periodically perturbed oscillations are quasi-periodic and contain two independent time scales. However, a well-timed breathing of the velocity field at the right amplitude can give rise to another stable periodic orbit, a limit cycle, whose frequency will either coincide with the frequency of forcing or be rationally related to it. This will mean the occurrence of a forced synchronization. Transition from non-synchronous to synchronous oscillations can be possible when the control parameters of the forcing are being changed. Suppose we choose the value of forcing frequency omega, which is different from the frequency of the unforced oscillations. It is intuitively clear that if the forcing is weak, meaning that the value of B is very small, it is quite unlikely that it will be possible to achieve synchronization. However, if we increase the forcing amplitude, our chances to achieve synchronization improve. Assume that we fix the frequency of forcing and gradually increase the forcing amplitude from 0 to some finite value. Synchronization can be achieved through one of the three general mechanisms. These are phase of frequency locking or suppression of natural dynamics, which we will consider within this lecture. The third mechanism is through the so-called homoclinic synchronization, which we will not consider here because it is not as popular. These three mechanisms have different manifestations in the language of physics and of mathematics. Physically, on the way to synchronization, the power spectra of the signals coming from interacting systems undergo different transformations. Mathematically, to achieve synchronization, different bifurcations need to take place. In this lecture, we will consider phase locking and suppression for the simplest case of a one-to-one forced synchronization only. This slide illustrates the one-to-one frequency locking in a periodically forced van der Pol oscillator. The figure to the left shows a two-parameter bifurcation diagram whose coordinate axes are the parameters of external forcing. The horizontal axis is the forcing frequency and the vertical axis is the forcing amplitude. The green area highlights the area where frequency locking occurs. The tip of the green area, which touches the horizontal axis, is located at the frequency of natural oscillations of the unforced system, called natural frequency. To explain what happens on the way to synchronization, we fix the forcing frequency at the value corresponding to the position of the vertical blue line. Therefore, the forcing frequency is slightly larger than the natural frequency. Then we only change the value of forcing amplitude. The left-hand panel of the slide shows various characteristics of oscillations in the system, and each row corresponds to a different value of the forcing amplitude. The first column shows the signal x of t coming from the system. The second column shows the power spectrum of this signal, and the third column is the Poincare section of the system. The position of the forcing frequency is indicated on the spectra by the green dashed line. When the forcing amplitude is 0, which means that the system demonstrates only natural oscillations, these oscillations are perfectly periodic. This is evidenced by the signal x of t, whose amplitude is constant, by the presence of only a single peak in the spectrum, and by the Poincare section representing a point, which is the section of a limit cycle. Now, when the forcing amplitude is slightly larger than 0, oscillations in the system become quasi-periodic. This is visible in all parameters of oscillations. In the signal x of t, whose amplitude now slowly fluctuates, in the spectrum, in which there are two independent frequencies. One corresponds to the peak at the forcing frequency, and the other to the peak to the left of it. This second peak occurs thanks to the presence of natural oscillations in the system, whose frequency is now shifted towards the frequency of forcing. The other peaks to the left represent the so-called combination frequencies and are the result of a nonlinear interaction between the two main timescales. The Poincare section is a closed curve, which represents an ergodic invariant torus. The empty circle in the middle is the unstable cycle, which is the trace of the stable cycle which existed in the phase space of the unforced system. This is not synchronization. When the amplitude of the forcing grows larger, the oscillations in the system become almost periodic, but not quite. In the spectrum, the peak at the frequency of forcing becomes the dominant one, but there are still other spectrum peaks which represent natural oscillations. One can see that the second highest peak, which is immediately to the left of the peak at the forcing frequency, came very close to it, which indicates that the dominating frequency of natural oscillations is very close to the forcing frequency. However, oscillations in the system are still quasi-periodic, and the Poincare section of the stable oscillatory regime is still a closed curve. Note that the radius of this closed curve is the same as its radius at a smaller forcing amplitude, shown just below. What is different is the popularity of different areas in the section. Some areas are visited more often, and these areas are covered by the points densely, and the area in the lower left part of the section is visited rarely, so the points there are not so dense. When the amplitude of forcing becomes large enough, and in the bifurcation diagram the blue vertical line crosses the boundary of the green synchronization area, synchronization occurs. Now the system demonstrates purely periodic oscillations at the frequency of forcing. This is particularly well visible in the spectrum, which now contains only one peak at the forcing frequency. As to the Poincare section, it has an interesting structure. Black filled circle indicates the position of the section of the limit cycle, whose spectrum is shown to the left. This is the stable oscillatory behavior which we observe in numerical simulation when we set arbitrary initial conditions. However, besides the stable cycle, the phase space of this system contains some more objects. Firstly, there is a saddle cycle shown by the gray-filled circle. Secondly, there is a torus marked by gray line, on whose surface lie both the stable and the saddle cycles. This is essentially the same torus which was ergodic in the absence of synchronization and was shown by black in the picture just below. But the transition to synchronization occurred as a result of a saddle node bifurcation on the surface of this torus, which led to the appearance of a pair of cycles, a stable and a saddle one. The saddle cycle is non-attracting, so the phase trajectories do not converge to it. If when solving our differential equations we set the initial conditions at random, we will not notice the existence of either the saddle cycle or the torus, which in this case is called resonant. Now, it is their invisible presence which allows one to explain how the transition to synchronization occurred. If we increase the forcing amplitude even further, the oscillations in the system remain periodic with the forcing frequency. So from the viewpoint of numerical simulation, from arbitrary initial conditions, nothing changes. However, there is an interesting transformation of the unstable, invisible objects. Namely, the unstable cycle, denoted by an empty circle, approaches the saddle cycle. When the vertical blue line in the bifurcation diagram crosses the upper boundary of the green area, these two unstable cycles collide in a saddle node bifurcation and disappear. As a result, the torus disappears together with them. So the only object left in the phase space is the stable cycle. Note that for an observer who only looks at the attracting solutions of differential equations, this major event goes completely unnoticed, and all he or she sees is the same periodic oscillations at the frequency of forcing. Overall, the behavior of spectra on the way to synchronization explains why this mechanism is called frequency locking. It is because when we initially increase the forcing amplitude, the frequency of natural oscillations comes closer and closer to the frequency of forcing until it coincides with it completely. So the external forcing locked our natural oscillations. If while staying inside synchronization area we modify the forcing frequency, the frequency of oscillations in the system follows the forcing frequency because it is locked by it. In the previous slide, we illustrated transition to synchronization in a dynamical system represented by differential equations. To prove that this is not just a mathematical trick, but a genuine physical phenomenon, here we illustrate the same transition in an electronic experiment. We take an electronic circuit demonstrating self-oscillations of voltages and currents and apply a periodically oscillating voltage to it. The forcing frequency is fixed and the forcing amplitude grows from the bottom to the top. All pictures here represent snapshots from a physical measuring instrument called an oscilloscope. The first column shows the traces of voltages. The one fluctuating with a larger amplitude corresponds to the oscillations in the circuit, and the trace with a smaller amplitude to the applied voltage. In the middle column, the spectra of the forced oscillations are given, and in the right-hand column, there are phase portraits of oscillations on the plane of two voltages in the circuit. When the forcing amplitude is zero, the circuit demonstrates periodic oscillations. The forcing frequency is formally shown on the lowest spectrum by the yellow vertical line to emphasize that it is different from the frequency of natural oscillations. When the forcing amplitude grows to a moderate amount, one can see already from the oscillating voltages that they are not synchronous. Here oscillations are quasi-periodic and the spectrum contains a peak at the forcing frequency and a peak corresponding to natural oscillations. This second peak has moved its location towards the forcing frequency. At the same time, there are many smaller peaks at combination frequencies. Obviously, this is not synchronization. When the forcing amplitude becomes larger, oscillations become almost periodic but not quite. Although the high spectrum peak is now at the frequency of forcing, and the second in height is very close to it, still there are many combination frequencies in the spectrum, which confirms that oscillations are quasi-periodic. Also, the phase portrait is not a closed curve, but a torus with a noticeable thickness. Further increase of the forcing amplitude finally leads to one-to-one synchronization, for which there is every evidence. The voltages are clearly synchronous, the spectrum contains only one peak at the forcing frequency, and the phase portrait is a limit cycle. This transition to synchronization had all features of frequency locking, because while approaching the boundary of synchronization threshold, the frequency of natural oscillations was gradually approaching the frequency of forcing. Next, we consider the second mechanism of synchronization, the suppression of natural dynamics. Firstly, we consider what happens in a mathematical model of a self-oscillator, the forced van der Pol system. Here, the meanings of all the graphs are the same as in the similar slide illustrating frequency locking, which we just considered. To observe suppression, we need to introduce a larger detuning between the system and the forcing. Namely, the forcing frequency should be at a larger distance from the natural frequency, as shown by the vertical purple line, and also by the green dashed line in the spectra. At zero forcing, there are periodic natural oscillations in the system, which are represented by a limit cycle. So the start is exactly the same as with locking. Here the arrows, pointing from left to right, start at the pink line at the height that indicates the amplitude of the applied forcing. When we set some moderate forcing amplitude, oscillations are quasi-periodic and are represented by an ergodic torus, almost like in the case of locking. However, there is a considerable difference from the locking mechanism. Here, the spectrum peak corresponding to natural oscillations does not move closer to the frequency of forcing as compared to the unforced case. It stays at the same position. Further increase of the forcing strength leads to an increase in the height of the spectrum peak at the forcing frequency. With this, the peak at natural frequency continues to keep its distance. At the same time, the ergodic torus becomes thinner, which can be seen in the smaller radius of its Poincaré section. Further strengthening of the forcing makes the peak at the forcing frequency the dominant one. The peak at the natural frequency becomes only second in height, but is still far away from the forcing frequency. With this, the torus shrinks considerably and approaches the unstable cycle marked by empty circle. At an even larger forcing, synchronization takes place, which is clearly seen from the behavior of the signals in the left-hand column and from the spectrum. Interestingly, unlike in the case of locking, inside synchronization region there is no torus anymore. The ergodic torus disappeared as a result of colliding with the unstable cycle in an analog of an inverse Andronov-Hopf bifurcation. It left behind only the cycle, which has become stable as a result of this collision. This synchronization mechanism is called suppression of natural dynamics, because on the way to synchronization, the spectrum component corresponding to natural oscillations was gradually disappearing, while giving way to the component corresponding to forcing. The power was gradually taken away from natural oscillations to the one occurring thanks to forcing. However, the frequencies of these diverse oscillatory modes almost did not change. Here, we illustrate the transition to synchronization via suppression of natural dynamics in an electronic experiment. All panels have the same meaning as when we considered frequency locking. Without going into much detail, it is sufficient to say that all stages considered in the previous slide, which were present in a mathematical model, are observed in the physical experiment too. To summarize, we considered two most general mechanisms of synchronization: frequency locking and suppression of natural dynamics. We also demonstrated that they are not merely a mathematical trick, but a real physical phenomenon. I would like to acknowledge professional and technical assistance from Olga Sosnovtseva and Dmitry Pasnov.